Okay, welcome back Physics 30s to our next lesson. This is 1.4 and today we're going to be looking at conservation of momentum. Okay, so first let's consider this astronaut, and he's out in space working on his spaceship. And as he's working, he begins to drift away from the spaceship. This is a problem because now he doesn't have any way to get back. He doesn't have a tether, there's nothing to grab on, and he's kind of stranded in space. So he's pretty frustrated with himself that he forgot to tie off to the spaceship. And in his frustration, he turns the other way and he whips his hammer into outer space, frustrated with his mistake. But then all of a sudden, he bumps into the spaceship. And to his surprise, he is back to safety as he can grab on to the spaceship. He's not quite sure how this happened, but he's very happy to be back to his ship and to safety. To help him understand what went on here, we have to consider Newton's third law. Newton's third law is that for every force, there's an equal and opposite force. I covered this in a little bit more detail in a previous video for Physics 20, so I'll put a link here to that video. You can rewatch it, but here's a couple clips from it. Every force, there's an equal and opposite force. Okay, so in this video, it's going to show a gun shooting, and there's going to be a force applied to the bullet, and so we're going to see if the bullet is going to apply a force onto the gun. And we watched the video, this is in slow motion that I recorded, and when the bullet is fired, we see it is accelerated forwards, and the gun is pushed backwards. But this actually applies to almost any scenario when you're trying to get moving. Think of a push-up. When you do a push-up, your body moves up, but what direction do you apply a force? You apply it down. Same is true with a pull-up. When you pull your body up, what direction do you apply the force? You apply the force downwards. You pull down on the bar is attached to the earth, and it applies an equal and opposite force to you, which is going to lift you up. And so in application to the astronaut, he's holding a hammer and he throws it in this direction. He applies a force to the hammer this way, so based off Newton's third law, there's an equal and opposite force that the hammer applies to him. So that pushes him back this way and moves him closer towards the ship. But now in this lesson, we're going to see how Newton's third law applies to momentum. And it applies to this big idea, the conservation of momentum, which says that in an isolated system, momentum is conserved. This means that it's not going to change from the start to the end. However much momentum we have at the start has to equal the momentum that we have at the end. Now, looking at this definition, we have to look at what an isolated system is. This means that there's no external forces. Well, what's an external force? An external force is a force from sources outside of the object that we are looking at. So if we were looking at the hammer and the person, things outside of this would be things like friction, most commonly in air resistance. Fortunately, these weren't here in space, but in other examples we'll see on Earth, they could play a factor. Internal forces are opposite to this in that they're forces exerted within the system or by the objects we're looking at. And I put Newton's third law there. So if we're throwing an object away or objects are bouncing off of each other, the forces they're applying to each other are internal. Now, if we're considering just internal forces and there's no external forces, momentum is conserved in all collisions. To get a better idea of these, let's take a look at this example where we have two vehicles and they're going to be colliding. So the truck and the silver car crash into each other. Now, looking at the forces going on in that collision, the blue truck applies a force to the silver car in this direction, and the silver car applies a force to the truck in this direction. Those are forces applied by the objects involved in the collision, so those would be considered internal forces. External forces here would be friction on the ground. After they bounce, there might be some friction resisting that movement between the tires and the ground. That's occurring from the road or an external force, and so those are considered external forces of friction and sometimes air resistance. So if we're dealing just with internal forces, momentum is going to be conserved in all collisions. Now, you might be thinking that's all well and good, but when do you only have internal forces? When do you have there no friction or no air resistance playing a factor? It seems like there's always involved here on Earth. Which is true. However, these external forces are often considered negligible compared to the internal forces, so we can still use conservation of momentum in a lot of collisions here on Earth. So what this is trying to say is, imagine we have two cars and they smash together like we had in that diagram. The forces applied to each car are really high. The amount of force from friction on the road comparatively is really small. So if you had a significant amount of friction and not much internal force, yeah, that would make it so we couldn't use conservation of momentum. But if it's very tiny compared to the big internal forces we're looking at, we can consider them negligible as they won't affect our answers very much. So that can be a little bit tricky on tests when it's asking about those. You can't say we just ignore all external forces, but if they're so small compared to the internal forces, we're going to consider them negligible. But now let's look at how we would calculate this. Having conservation of momentum, this is basically saying that the momentum at the start, or PI, momentum initial, is equal to PF, which is momentum final. This often involves two objects colliding, so I'm going to say the momentum of object A at the start plus the momentum of object B at the start is equal to the momentum of object A at the end plus the momentum of object B at the end. This is how I normally write it and like to solve for these questions best, and then we just plug into all those P's with MV. So all our MVs at the start equal all our MVs at the end. But there's another way we can rearrange this that shows us how it relates to Newton's third law. I'll switch to green here. If I'm going to try and get all the A's on one side, I'm going to subtract PAI over here. And I have PAF minus PAI, my final minus initial. And then if I'm going to get the B's on the same side, I'm going to minus PBF over here, minus PBF over here, cancels, and I have PBI minus PBF are equal to each other. So this is looking at the changes in momentum for B and A. So we usually look at this as final minus initial. So for this side over here, I'm just going to flip it, which is going to make it so that there's a negative on the other side. I'm going to flip the signs here. So it's negative PBF minus PBI is equal to PAF minus PAI. Now that I have those final minus initial, I'm looking at the change. So I'm going to just simplify this to the change in momentum of B, negative, is equal to the change in momentum of A. This shows us a relationship to Newton's third law. The change in momentum of B is equal but opposite to the change in momentum of A. And the way that this relates to force is before that we saw that force times time gave an impulse or a change in momentum. And this makes sense because our impulse or change in momentum was equal to our force times our time. Again, we saw that from before. And we have two objects that are traveling at each other and they collide, they apply an equal and opposite force to each other. So if the forces are the same, but in opposite directions, the time that they're actually in contact with each other, when they bounce off of one another, the time that they're in contact is the same for both of those objects. If I put in times t here, these two values should be the same, but just opposite based off that sign. So because they apply an equal and opposite force for the same duration of time, their impulse is the same. So therefore the change in momentum of one is equal and opposite to the change in momentum of the other, so they cancel out to be zero. There's no change in momentum in the system. Hopefully that makes sense for you. Let's apply it to these three scenarios. I'm gonna use some pretty easy numbers just to get across the idea. There's three types of collisions we can have. We have an explosion, which is where something's gonna be breaking apart or pushing against another, kind of like the hammer and the astronaut. So let's say we have this object and it explodes and it breaks into these two pieces. How would momentum be conserved? Well, to start, momentum was equal to zero. It was just stationary. But now we have movement, or we do have momentum of these pieces. It seems like it wouldn't be conserved, but here's where we have to remember that momentum is a vector. So let's say that this piece over here is moving with a momentum of P is equal to 10 Newton seconds. Positive in that direction. That means the other piece here has to be moving this way with P is equal to negative 10 Newton seconds. So we have positive 10, negative 10, that total is zero. And our starting total was zero, so momentum is conserved. Let's look at another example that I call hit and rebound. This is when we're gonna have objects hitting into each other and then bouncing off. In this case, they're actually going in the same direction. So I have them moving together, bouncing, and continuing in the same way. So I'll try and illustrate that. A comes in and hits B, B comes in and hits A, and they bounce, and then they're gonna end up moving still in this direction, but at different speeds. So let's say that off the start, I'll just put this back, that A has a momentum of 10 Newton seconds, okay? And B has a momentum of negative 2 Newton seconds because it's moving in the opposite direction. Then they come together and collide, and again they bounce and they end up both moving in the same direction. Let's say afterwards A has momentum because it ran into B there, it decreased its momentum to 6 Newton seconds. What would it be for B? Well, at the start, we had a total of 10 plus negative 2. So we had 8 as our value for momentum at the start. Well, it needs to be 8 at the end. So we have positive 6. What does B have to be? Positive 2 Newton seconds. So it's going in the opposite direction. Now there's some mass changes there, so we'd have to know what the masses were to find the velocities, but you kind of get the overall concept. The last type we're going to look at is hit and stick. This is where we have two objects collide and then they stick together as one mass. So let's have A and B come together and say B stationary, they hit, and then they move together as one. Let's put that back and say that initially A had a momentum of 10 Newton seconds and B was 0. The total off the start is 10. After they collide and move together, the momentum of them as one object needs to be 10 to be the same as our start. Now that seems fairly straightforward. You started with 10 and then you end up with 10. But the thing that changes is that now that a higher mass, those two masses stuck together, are moving with a momentum of 10. So if the mass went up, our velocity must be down. So they're going to move together as a group going slower than A was initially. Again, we could calculate that if we knew the masses. That's the three types of examples that we're going to look at. So hopefully the concept from those previous examples makes sense. Now let's do some practice calculations. Okay, so this first example is that a satellite's in space and it is stationary. And it fires its thrusters and it sends 2.5 kilograms of hot gas to the left, and the 50 kilogram satellite moves at 10 meters per second to the right. What is the speed of the hot gas? Okay, so let's start with our satellite right there, and now let's put the hot gas right there coming out the back of the rocket. Okay, so it's nice that there's no friction or air resistance here in space, so I know that there's going to be no external forces. I'm just going to write Pi is equal to Pf off the start, saying momentum is conserved. Now at the start, the whole system was stationary. The gas and the satellite were sitting there in space, and then they shot away from each other. But at the start, there was no momentum because there was no velocity. At the end, there is. We have the momentum of, let's say, the gas, right, at the end, plus the momentum of the satellite at the end. I'll just put a G here for gas and S there for satellite. Now, it's also important that we keep track of direction. I'm going to call this way positive and this way negative. All right, so now let's plug in. We say 0 is equal to, momentum is m times v, so the mass of the gas is 2.5 kilograms times its velocity, which we don't know, so I'm just going to put v there, plus the satellite, which is 50 kilograms, times 10 meters per second. So here I'm getting 2.5 v, because I don't know that, plus 500 Newton seconds, or kilogram meters per second. And so to solve for v, I'm just going to subtract the 500 over, and I'm just going to write over here, I get negative 500 Newton seconds is equal to 2.5 v. Next, I just divide by the 2.5, and I'm getting 200, negative 200 meters per second for the velocity, which is a pretty high speed, and that's because it's so much less mass. To get the heavy satellite going 10 meters per second, we need the light gas to go much, much faster and in the opposite direction. Let's take a look at one more example. This one's going to involve a baseball and a baseball bat. It says a 0.15 kilogram baseball is traveling at negative 30 meters per second. Good to note that it's negative. When it collides with a 1 kilogram bat traveling at 12 meters per second, the ball and the bat collide. After the collision, the bat is traveling at a much slower speed of 3.5 meters per second. Again, positive. What is the speed of the baseball? At this point, given what you know from this lesson and previous lessons, I'd like you to pause the video, see if you can solve this one on your own, and check back in to see how you did. Okay, let's see how that went. You might have been thinking, well, there is going to be some air resistance involved in this because we're on Earth. However, I hope we noted that the forces applied by the ball and the bat to each other are much higher than the air resistance in that short time of the collision. So we can assume that air resistance is negligible and Pi is equal to Pf. Now in this case, we have some momentum at the start and momentum at the end, and there are two things. So I'm going to start writing what I wrote similar to that blackboard, where I have the two objects, P, let's go with B for baseball bat, initial, plus P, I would go B for another baseball. Let's just put C, because I guess the baseball would be like a circle. So that's the initial momentum of the bat and the circle, and that equals the momentum of the bat final plus the momentum of the circle final. Now just to illustrate this, I'm going to draw tiny diagrams of the bat and the ball for this scenario. Okay, so there's my little diagrams of them. We start with the initial momentum of the bat. I'm going to put mv for calculating that, plus the initial momentum of the baseball, which is going to be in the opposite direction, or C there for the circle, mv, and then equals, so on the other side, or the final side of this equation, is going to be mv of the bat at the end. It's moving slower, and we're trying to solve for the v of the baseball or the circle there. So let's plug in what we know. We know that it is a 1 kilogram baseball bat, and it's initially going at 12 meters per second, plus the baseball is 0.15 kilograms, and it's going at negative 30 meters per second. Sorry, it's a bit small. And then the bat at the end, still 1 kilogram, and it's going at 3.5 meters per second, plus the 0.15 kilogram baseball, and we do not know the velocity. So let's plug in some of these numbers, make it a bit easier. We start with 12 Newton seconds for the bat, negative 4.5 for the baseball, and then at the end the bat has 3.5, and we have 0.15 v. We're trying to solve for the velocity. Let's take 12 minus the 4.5 and then minus the 3.5 over, and then we get a number of 4 left over for the momentum of the baseball, and that's equal to 0.15 v divided by 0.15, and I'm getting a number of 26.6 repeating meters per second. In our question, it looks like there was 2 digits throughout the whole time, so I'm going to round that to 27 meters per second. Important to know that it is positive, so it is going the opposite direction and that it was going at the start, and that would be our final answer. So I hope that video made sense for you. Thank you so much for watching. Let me know if you have any questions, try the practice questions, and I'll see you in the next video.